Welcome back to The Explainer. Today, we're popping the hood to unpack the fascinating, multi-layered architecture of task-based dialogue systems. We interact with digital assistants literally every single day, right? But have you ever actually stopped to wonder how a machine processes your spoken requests and turns them into real-world actions? Well, today, we're opening up the black box to see exactly how these conversational engines operate. Think about it for a second. When you ask a virtual assistant to book a flight or find a nearby restaurant, what is actually happening behind the scenes? How on earth does it take the chaotic, completely unpredictable nature of human speech and transform it into a confirmed airline ticket or a calendar appointment? The secret lies in a concept called a task-based dialogue system. It relies on a super intricate pipeline of components that translates your messy speech into highly structured machine actions. And it does this using knowledge structures called frames. Honestly, it's best to think of a frame as a mental checklist. The computer uses this checklist to guarantee it has every single detail required to actually pull off what you're asking it to do. To really see how this works, we're going to follow a single user request right through this pipeline. We'll start with the anatomy of AI assistants, move into extracting intents and slots, tracking the dialogue state, setting conversation policies, and finally, generating natural responses. Okay, part 1, anatomy of AI assistants, or the building blocks of conversation. So these systems run entirely on what we call frames and slots. Basically, imagine the machine is holding a giant game of Mad Libs, and it desperately needs you to fill in the blanks. A complete set of these frames is called a domain ontology. Just like in Mad Libs, where you have to provide a noun, verb, or a place to finish the story, the dialogue system has a blank template. Its one and only goal during your chat is to figure out which words from your sentences belong in which blanks. Take a basic air travel frame as an example. The system knows exactly which slots it needs to fill, and notice how each slot has a very specific semantic type. If it needs an origin city, it absolutely knows it's looking for a value of type city, like Boston or Hong Kong. If it's missing that specific piece of the puzzle, it has a pre-programmed or dynamically generated question ready to fire off, something like, "From what city are you leaving?" just to prompt you for that exact missing detail. Moving right along to part 2, extracting intents and slots. Essentially, making sense of your words. You've spoken a request, and now the system has to figure out which Mad Libs form to grab. This happens in the spoken language understanding phase, and it breaks down neatly into 3 sequential tasks. First up, domain classification. The system has to realize you're talking about air travel, not setting a morning alarm. Second, intent determination. Within travel, are you trying to book a new flight or cancel an old reservation? And finally, slot filling. Parsing your sentence to pull out the specific dates, times, and locations to fill those empty blanks we just talked about. This is wild when you think about it. You can throw a complex, natural sentence at the machine, and it instantly flattens it into structured data points. Say you tell it, "Show me morning flights from Boston to San Francisco on Tuesday." The system quickly flags the domain as air travel, and the intent as show flights. Then it just plucks out the data. Boston goes to origin city, San Francisco to destination city, Tuesday to origin date, and morning to origin time. Boom! Conversational English is instantly turned into a strict data table. Now, how do engineers know if this extraction actually worked? They track 2 very distinct metrics to compare overall success against fine-grained accuracy. The task error rate is the big picture. Did you actually get on the right plane? But the slot error rate is way more granular. Think about it. You might have successfully booked a meeting with your boss, which is a task success, but if the system put it in room 104 instead of 105, well, that's a slot error that could cause some real panic. Both of these metrics are absolutely crucial for improving how these assistants learn. All right, part 3, tracking the dialogue state, or remembering the context. Because it's not enough to just understand one sentence in a vacuum. The machine has to remember the entire conversation. Enter the dialogue state tracker. It monitors your constraints across the whole chat by categorizing your inputs into specific dialogue acts. When we talk, we're performing actions, right? If you say, "I want Italian food," you are performing an inform act. If the system replies, "Is the price reasonable?" it's performing a confirm act. By tagging every single back and forth with these labels, the system keeps a running summary of the conversation's history. But hey, we've all been there. What happens when a machine completely botches it and you have to issue a correction act? This is actually a massive headache in speech recognition because humans react very predictably to being misunderstood. This is Absolutely fascinating. When we get frustrated, we do this thing called hyperarticulation. We speak louder, we stretch out our vowels, we pause awkwardly between syllables, and ironically, this completely breaks the system's acoustic models because you're deviating from the normal conversational data the machine was trained on. Trying to make yourself clearer actually almost guarantees the computer is going to misunderstand you a second time. So, once the system figures out what you want or realizes it's totally confused, it enters phase 4, setting conversation policies, or deciding what to say next. The machine is constantly playing this balancing game between explicitly double-checking everything versus implicitly moving things forward. If it uses explicit confirmation, it's super safe. You can just say no if it's wrong. But it makes for a painfully slow, robotic conversation. I have you going to New York on September 21st. Is that correct? Implicit confirmation feels much breezier, kind of like a human repeating a detail in passing. When do you want to travel to Shanghai? But if the system misheard Shanghai and you don't catch it, the whole task is toast. To figure out how to handle this without driving you crazy, the system relies on a tiered confidence threshold. The speech recognizer literally scores its own confidence in what it heard. If it's totally lost, below the alpha threshold, it admits defeat and asks you to repeat. If it's fairly confident, it confirms explicitly. Higher confidence gets an implicit confirmation. And if it's crystal clear, above the gamma threshold, it just accepts the info and moves on without even asking. And that brings us to the final step of our journey, generating natural responses. It is finally time for the machine to talk back. Obviously, the AI can't memorize every single restaurant name or flight number on the planet. So it uses a brilliant workaround called delexicalization. It strips the specific nouns out of its training sentences and swaps in generic placeholders. This lets the system learn the grammar and flow of a natural recommendation without getting completely bogged down by millions of random proper nouns. What happens is the model spits out a generic template and then quickly swaps the actual data back in. This is called relexicalizing. It maps the data it pulled from its database directly into those placeholder slots right before speaking the sentence out loud to you. It's just a beautifully efficient way to generate infinite combinations of natural-sounding sentences. To really appreciate how elegant this all is, we have to look back at how it evolved. It started with simple pattern-matching chatbots like Eliza in the 1960s. Then, in 1977, the GUS system introduced the exact frame-based slot-filling paradigm we've been talking about today. By the 2000s, reinforcement learning was optimizing these decisions. And by the 2010s, this foundational architecture finally scaled up to power the voice assistants sitting in our pockets right now. So, I want to leave you with one final, provocative thought about where all this is heading. We've just seen how meticulously structured this process is, a pipeline of acts, frames, and slots. But as modern neural networks start to blur those lines, moving away from rigid templates and toward free-flowing language generation, we're entering a whole new era. When conversational AI gets so fluid that we can no longer see the Mad Libs form underneath, what will that mean for human connection? What happens when we genuinely can't tell if a machine is just running a clever script or if it's truly beginning to understand us? Thanks for exploring the mechanics of conversation with us today. Keep asking questions, and I'll catch you in the next explainer.